So imagine a game so complex it has more possible moves than there are atoms in the entire known universe. And now imagine an algorithm that actually learned to master it. That's what we're talking about today, the incredible, elegant thinking that finally conquered the ancient game of Go. And that's not just some dramatic hook to get you interested. It's the real, honest to goodness challenge that had AI researchers stumped for decades. The number of possibilities in Go is it's so vast, it's mind-bogglingly huge. You literally can't calculate every possible outcome. It's impossible.
Okay, to really get a feel for this, let's compare it to a game we all know, chess, right? In a typical turn in chess, you might have, 35 different moves you can make? But in Go, that number just skyrockets to an average of around 180. Think about that. It's like trying to navigate a maze where every single step you take suddenly opens up 180 new paths. That is why Go was such a tough nut for computers to crack for so long.
Yeah, this incredible complexity is exactly why Go wasn't just another game on the list. For the folks in AI research, this was kind of like the final frontier. To conquer Go, well, that meant you were solving a really fundamental problem in how machines could learn to think strategically, How they could make smart decisions when faced with just an overwhelming amount of choice. So, how on earth did they finally crack the code? Well, the big breakthrough came from an algorithm that didn't even try to brute force its way through everything. No, instead, it learned to play intelligently. It learned to focus its attention. And this is the story of the Monte Carlo Tree Search. The whole idea behind Monte Carlo Tree Search, or MCTS, is actually surprisingly elegant. Instead of trying to analyze every single possible move, it just plays the game, over and over and over, thousands of times a second. It runs these super fast, totally random playouts all the way to the end of the game. And all the while, it's keeping track of which opening moves led to the most wins. It uses that data to get smarter with every single game it plays. And this whole thing happens in a continuous rapid-fire loop. It's a four-step dance. First, it selects the most promising path it's already looked at. Then it expands its knowledge by trying just one new unexplored move. Next up, it runs a lightning-fast random simulation from that new move to see how it might turn out. And finally, and this part is absolutely crucial, it backpropagates the result, whether it was a win or a loss, all the way back up the decision tree, updating its entire strategy with what it just learned. Then it does it again and again, thousands of times. The real genius of this algorithm is this constant balancing act it's performing. It's always asking itself, should I exploit what I already know works well, or should I explore a totally new, untested path that could be a hidden gem? It's kind of like deciding between going to your favorite restaurant that you know is great, or trying that new place you've heard amazing things about. That tension, right, between the safe bet and the exciting unknown, that's the secret sauce to its intelligence. And this is what makes MCTS so ridiculously efficient. See, older algorithms would waste so much time analyzing every single bad move, just as much as the good ones. But MCTS, it learns to focus its energy on the stuff that looks promising. The branches of its search tree that look good get explored really, really deeply, while the weaker moves, well, they get identified pretty quickly and are mostly just ignored. Okay, so mastering a game where you can see everything on the board, that was huge, but it was really just the beginning. The next big challenge was figuring out how to adapt this powerful method to situations where some of the crucial information is actually hidden from you. Right, so think about it. Games like Go and chess are what we call perfect information games. You can see the entire state of the game, all the pieces, all at once. But then you have imperfect information games like poker, where you can't see your opponent's cards, or a lot of video games with a fog of war that hides parts of the map. Suddenly, the problem gets much, much harder. So that brings up a massive new hurdle for any search algorithm, right? I mean, how can you possibly find the best move if you don't even know for sure what the true state of the game is? Well, the solution is this really clever trick called determinization. The algorithm basically says, all right, I don't know what cards my opponent has, so I'm just going to imagine a dozen possible hands they could have, and I'll run my search through all of those different what-if scenarios. It's brilliant, really. It turns one huge, uncertain problem into a bunch of smaller, solvable ones. And all of this brings us to the moment that really, truly changed the game for AI forever. This is when that powerful search algorithm we've been talking about got combined with the incredible pattern recognition power of modern deep learning. And what came out the other side was something truly revolutionary. So back in 2016, DeepMind's AlphaGo didn't just tweak MCTS, it gave it superpowers.
By fusing the search algorithm with these things called deep neural networks, they fundamentally changed how the program sees the game. It gave it something that, well, it looks a whole lot like human intuition.
So, how did this actually work? Well, think of it like this. AlphaGo gave MCTS two new, specialized brains, and each one had a critical job to do. The first one, the policy network, acted kind of like an expert's gut feeling. It would look at the board and instantly suggest just a small handful of really promising, high-quality moves.
Then you have the second brain, the value network, which was a master evaluator. It could just glance at any board position, no matter how ridiculously complex, and immediately estimate the probability of winning from that state. So you put them together, and what do you get? You get a search that is unbelievably efficient. The policy network prunes away all the dumb moves, and the value network lets it judge a position without having to play the whole game out in its head. It's an amazing 1-2 punch. And the result? It was historic. I mean, as the source material points out, this was seen as a breakthrough not just for the game of Go, but for the entire field of artificial intelligence. AlphaGo had achieved a level of strategic understanding that, honestly, many experts thought was still decades away.
Okay, so this is all really cool, but why does any of it matter outside of a board game? Well, here's the kicker. The very same intelligent decision-making process that conquered Go is now being used to solve some of our most complex real-world challenges.
Because when you think about it, the ability to navigate a massive sea of possibilities, to intelligently balance what you know with what you don't, that's a universal problem-solving skill. And that is exactly what MCTS excels at, whether it's on a Go board or inside a sprawling, complex logistics network.
And we're already seeing this logic in action all over the place. It's optimizing complex delivery routes for packages, it's planning the incredibly delicate steps needed to synthesize new, life-saving molecules, it's designing optimal security patrols, it's even helping guide robotic planning. In every single one of these cases, it's that same beautiful principle at work, an intelligent search, balancing exploration and exploitation to find the absolute best solution in a world of nearly endless options. So it all started with an algorithm that was designed simply to master an ancient board game. But what it's become is a powerful general-purpose tool for navigating complexity in almost any field. And that leaves us with a really, really exciting question to think about. If this algorithm can master impossible games and help us discover new molecules, what grand challenge will it help us solve next? I mean, the possibilities, they're just as vast as the game of Go itself.